share to tab entire screen. Okay, share. So is my tab visible to all of you?
Yes, sir, it is visible now.
Okay, very good. Okay, so we were discussing angular momentum in our last discussion session. So let me just continue with that a little bit more. Okay. So if you remember, classically, you can define this angular momentum as r cross p vectors, and typically, in quantum mechanics, you take the components of this classically defined, quantity, and you just promote it to a operator. And this is our notation to symbolize that what we are dealing with is not a physical quantity, but it is an operator. So this is the quantization principle, where you start with the classical quantity, and you just upgrade it to become a operator. And of course, this by definition is basically the r vector operator cross p vector operator, and we are talking about the ith component of this. Okay, where typically the ri operator is simply xi. Remember, of course, in my notation, I belongs to either x, y, and z in the three spatial coordinates. So the vector representation, so this is, sorry, the operator representation. So what we are doing here is quantizing. And here we are looking at the representation. And one possible representation is that you just take the position operators to be the classical coordinate xi's, whereas you take the pi operator to be minus I h cross del xi, right? So this is basically the representation, and which is at the heart of what we call the uncertainty principle. Right? And what we did, in our last discussion was mainly to show you that if you take these operators Lx and Ly, and you find out what is the commutation relationship between them, and of course I am talking about the operators, they are given by these commutation results, right?
Sir, LZ.
Yeah, thank you. Yeah, so I should start. Is I h cross Ly, and the other one is Ly Lz I h cross Lx, right? This is what we discussed, and of course, the self commutation relationships just go to zero, and you can find out all the other commutation relationships by taking the antisymmetric combination of these things. The other thing that we discussed was introducing a total angular momentum operator, and then now from now on again I will start dropping the operator symbol because it is very clear from the context that we are talking not about the physical quantity but the corresponding quantized operator. So you can write this as Lx square plus Ly square plus Lz square. And what we found out is that if you take the commutation relationship of L squared with any Li, it was equal to 0 for all I belonging to x, y, and z. Okay. And the consequence of this thing, that the components of the angular momentum, see, this is a very, very special thing that doesn't happen, for example, for the components of a position vector or for the components of the momentum vector. Angular momentum is probably the first vector, classical vector, that you are encountering whose quantum mechanical interpretation is this weird in the sense that the components of the angular momentum vector themselves do not commute among each other, which leads to these two conclusions. I think we briefly mentioned them, and let me just again mention them over here. The first thing is that we cannot since the components of the angular momentum vector cannot be known with absolute certainty in the statistical sense. Therefore, we cannot draw a angular momentum vector for a quantum system. Because if you want to draw the vector, of course, you need to know what is Lx, what is Ly, and Lz. Only then you can give L a specific direction and magnitude, right? You need to know all the three components simultaneously. But in quantum mechanics, and this is not because of some uncertainty or anything, sorry, any experimental limitation. Just intrinsically, angular momentum is such and quantum mechanics is such that you cannot draw the L vector at all. Okay, so this is number one. And the second thing is that, of course, if you think of any state, psi cannot be a simultaneous eigenvector of Lx, Ly, and Lz. So if you have a system, I give you a quantum system, and you want to know some information about its angular momentum. Of course, classically, if I give you a system and I tell you what is the angular momentum, you will go ahead. You can compute, you can measure Lx, Ly, Lz, and therefore L square. You can measure everything, and you can give me that complete information. But in quantum mechanics, because the components of the angular momentum do not commute, you have this unique situation that if you have a quantum system, you can only know partially about its angular momentum. And you have to choose as to which are the things by which you want to describe angular momentum. Okay, so you have to choose operators for, I should say, incomplete. Okay, incomplete description of angular momentum, and it is just a convention. Okay, it's just a choice that people usually by convention is to choose the L square operator and the Lz operator. So typically, if I give you a quantum system, the maximum information about its angular momentum that you can have is that you can know its L square total angular momentum and any one component, and the convention is to choose Lz. Okay, this is the maximum that you can do. Okay, so if you have a angular momentum of a quantum system, so we want to know what can be known about the angular momentum of a quantum system. And I said the maximum that you can do, that you can tell me if the quantum system at best can be a simultaneous eigenvector of L square and Lz. That is the maximum that can happen. So if you give me a system psi, all that quantum mechanics allows you to know is that what is its eigenvalue with respect to the total angular momentum, and let's call it lambda, and what is its z component, eigenvalue Lz, and I don't know, let's call it mu maybe. Again, I'm trying to remember the symbols that are used in Griffiths, probably these are the ones. Okay. So this is the maximum. I can tell you lambda and mu. So lambda is kind of stands for the total angular momentum of the system, and mu kind of stands for the z component of the angular momentum of the system. Okay. Now the now the question is, what values can lambda and mu take? Okay. So we are asking, what are the possible values of lambda and mu? And to answer this question, we construct or we define a new operator which we call L plus minus, which is given by Lx plus minus Ly. Sorry, ILy. Okay. Just to understand, you guys have studied the harmonic oscillator problem using the ladder problem, the creation and annihilation operator. Have you done that?
Yes, sir.
Okay, very good. Then you will be very familiar with what I am doing. Of course, I hope you know what this notation means. L plus is Lx plus ILy, and L minus is Lx minus ILy. So I am just defining this new operator. And the first thing that I want to point out is that if we consider a state psi that is an eigenvalue or that's an eigenvector of L square and Lz with eigen. Okay, oh sorry, maybe just 1 second. Maybe we should first do the commutation and then come to this discussion. That would be better. Just sorry. So let's first do the commutation. Okay, by the way, let's just do that first. Okay. So let's look at what is the commutation relationship between L square and let's say L plus, just to start with. Okay. Maybe there's a better ordering in which we will follow things. Okay. So this is just the commutation relationship between this and by using the associative law, this is L square comma Lx plus I L square comma Ly, but we know that L square commutes with all the components, so without worrying we can just set these things to be to 0, and therefore we immediately find out that L square comma L plus is equal to 0. And I hope I don't need to do that. You can just now see very clearly that also L square comma L minus, using similar arguments, only everything is same except for the plus sign over minus sign, this will also be 0. So this is the first commutation relationship. The next one is Lz comma L plus. So let's do that. So this is Lz comma Lx plus ILy. Again, using the associative law, you have Lz comma Lx plus I Lz comma Ly. And if you just remember the commutation relationship that I wrote down over here, you can just read off these quantities. For example, this object becomes, let's just do it like this. This object becomes I H cross Ly, and then you have a plus I term, but then this object over here becomes minus I H cross Lx. Okay, I hope you agree with what is being written over here. So if I have this quantity, I have I H cross Ly plus, there's a plus I and a minus I, so it is H cross Lx. I can take I H cross common, and what I should get is, no, sorry, I should take just h square common. H h hat cut common, so it is Lx plus ILy, which is of course just H cross L plus, right? I hope this is clear. Now, if you just do the same thing, repeat the same thing with Lz comma L minus, I hope again I don't have to convince you, it comes out to be minus H cut L minus. Okay, so this is like the same thing. So please stop me if you have any doubts, if I'm making any mistake, or if you have any comments or questions to make. Okay. So these are the two set of commutation relationship which will be useful for us. So we have just wrote them down over here. That this L plus commutes with L square, and with the Lz component, it has this specific structure. Okay. Now, armed with these information, let us go on and look at what we were trying to do previously. Let's say that psi is an eigenvector of both L square and Lz with eigenvalues lambda and mu. Then we want to look at this object. Okay, we want to look at what would happen, what is the total angular momentum of the state which is given by L plus times psi. Okay, but we know that L square and L plus commutes, so this would mean that you can just exchange the L plus and L square and nothing should happen. Okay, so I have used the commutation relationship to exchange this object. Okay, this happens because L square comma L plus is 0. So using this fact, I am able to just write this. But I have already said psi is an eigenstate of L square with an eigenvalue lambda. So this is equal to lambda times L plus times psi. So the conclusion that we should draw from here is the following, that L plus psi is a state with L square eigenvalue lambda. Okay. So psi was an eigenvector of L square with eigenvalue lambda. Then L plus is also a state, which is an eigenvector of L square with an eigenvalue lambda. And again, I hope I don't need to convince you that if you do the same thing, L square with L minus psi, you will find out that this is just L minus L square psi, which is equal to lambda L minus psi. So again, the conclusion here is that L minus psi is also an eigenvector of L square with eigenvalues value lambda. Okay, very interesting, right? If psi is an eigenvalue, is an eigenvector of L square, then L plus minus of psi is also an eigenvector of L square. This is first thing. The next thing is, of course, to look at whether it's also an eigenvector of Lz and what is its corresponding eigenvalue. So we want to look at what is Lz, let's say L plus times psi. Now you have to use the commutation relationship. Remember what is Lz comma L plus, that is equal to L plus Lz plus H cross Lz, right, times psi. I hope it is clear how I am doing this. Just in case it is not, let me write it down explicitly. Remember Lz comma L plus we proved to be equal to H cross L plus. So if I just write this out explicitly, Lz L plus minus L plus Lz is equal to H cross L plus. Oh, sorry. Yeah, I made a mistake. Good. Sometimes doing things explicitly is good. This is L plus. So it implies that Lz L plus is equal to L plus Lz plus HL plus. Okay. So it's just trivial algebra. Now, if I look at the right hand side of that equation, what do I get? I get that Lz of L plus psi is equal to L plus Lz of psi plus H cross Lz of psi. But we already said that psi is also an eigenvector of Lz with an eigenvalue mu. So we find what is happening over here is mu plus H L plus of psi. So the implication from this is the following, that L plus of psi is also an eigenvector of Lz with eigenvalue mu plus H. And I hope I do not need to work this out. It should be straightforward, because everything is just a positive sign and a negative sign and nothing more. That if I now do Lz of L minus of psi, what I should get is mu minus H of L minus of psi, and this would imply that L minus of psi is an eigenstate of Lz with eigenvalue mu minus H. So what this
H or H cut?
H cut, very good, H cut. Everywhere it should be. If I missed it somewhere else, yeah. Everywhere it's H cut. Okay. Very good. So what we have found out is that these operators that we have defined, called L plus and L minus, are such, this L plus and L minus are such that if you act it on any state, of course, as we have already said, the maximum information about the angular momentum that you can have is this value of lambda and value of mu. Now, what this L plus and L minus does is that it never changes the lambda. If it is an eigenstate with an total angular momentum lambda, it still remains an eigenstate with an total angular momentum lambda. All that it does is that it shifts the z component by units of h prime, okay, or h cut, sorry, by units of h cut. So the situation is somewhat like this, that if you think about it, if you are looking at the Lz component, you expect that the values of Lz components are, if I call this mu, this is mu plus h cut, this is mu plus twice h cut, this is mu plus 3h cut, and so on and so forth. It goes up and goes down. These are the Lz components. And what we have learned is that basically, you can go up from any state to the next state by applying L plus, right? If you apply L plus, you will keep going up. Whereas if you apply L minus, you will be coming down. So this is the structure, it seems, that the z component of the angular momentum can take certain discrete values, and the values would always shift like mu, will be shifted from each other by an integer multiple of this quantity h cut. Okay. So if you go downwards, of course, it should be clear. This is mu minus h cut, this is mu minus 2h cut, and so on and so forth. Okay. So this is the structure. And this is for a state psi with total angular momentum but you see the Lz is one component of the total angular momentum. Okay, so immediately this operation of going higher and higher and higher in the angular momentum, or lower and lower and lower in the angular momentum, cannot continue forever. After all, well, by construction, L square is equal to Lx square plus Ly square plus Lz square, implying that Lz square is always less or maybe equal to L square. This has to be true, right? So this implies, what this is implying is a very important thing, that this raising or lowering of Lz cannot continue forever. Okay, there has to be a maximum Lz and there has to be a minimum Lz. Okay, it further implies that there has to be a Lz max and an Lz min. And basically, the Lz values range from this Lz mean to this Lz max with discrete intervals of h cut, because this has to happen. Now, how this can happen? What is the possibility that what we are saying is that you keep applying this L plus operator on a state, and you will go to a next state which has an z component of angular momentum enhanced by this amount h cut, but this cannot continue forever. So there will be one special state with maximum maximum z component of angular momentum. And this we are going to represent by, let's say, ZL, I don't know, Lz max. Okay. Just to make clear that this is a state at which the angular momentum, becomes maximum. Okay. Now, what we are going to say is that the z component, the Lz value of this Lz max, is going to be given by L times h cross of psi of Lz max, where L is some number. Okay, L is some number which tells us what is the maximum value of the z component of the angular momentum. And the fact this is maximum tells us that now if I apply the raising operator further on this, since this is maximum, you cannot go up higher up. So the only possibility is that it becomes 0. Okay. Or at least you go to a state which is no longer a part of your Hilbert space. which means that it is no longer a square normalizable. But let's not go into that nitty-gritty. What we are saying is that if you want to stay in on the Hilbert space in which quantum mechanics is well defined, L plus of psi of z do not belong to the set of state inside the Hilbert space. So it basically, you can basically consider it to be 0. Okay. Now with this understanding, let us try to figure out. So our question is, what is the total angular momentum of psi Lz max? So we want to find this thing out. So in order to do that, let's first find out what is L plus, L minus, L plus. Okay, this combination of operators. Let's just figure this out. So this is Lx plus, first is minus Lx minus I Ly multiplied by Lx plus I Ly. So if you do the multiplication, you will get Lx square plus Ly square, because there is a plus I and minus I. And then there will be a minus I Ly Lx plus I Lx Ly. Here I have to be careful about the ordering, because remember, Lx and Ly do not commute among each other. So you should keep the operators in the correct order. Now, this first thing can be written as L square minus L. Okay, if you want to be more explicit, maybe we write it like this: Lx square plus Ly square, and I'm going to add an Lz square and subtract an Lz square. I can always do that. And from the rest of it, I'm going to take plus I as common, and I will get Lx comma Ly. Right? Now this quantity, the Lx square plus Ly square plus Lz square, is simply L square minus Lz square plus I Lx comma Ly. Okay. Now this is L square minus Lz square, but you remember what is Lx comma Ly? It is plus I into I h cross Lz, right? So if I rewrite this thing a little bit, I can now write this L square as L minus L plus Lz square plus h cross Lz. I hope you will agree with this. Is this correct? Do you agree with this expression? I've just taken a... Okay, very good. So now that I've written it in this form, I am able to apply this L square operator using this on the psi Lz max state. Okay. Psi Lz max is now going to be given by L minus L plus of psi Lz max plus Lz square of psi Lz max plus h cross Lz of psi Lz max. You see, the nice trick that I've used is that I had no clue about L square. What is the property of L square on this Lz max state? Okay. But I had these two commutation relationship, right? I knew about how Lz operator acting on this psi, what it gives me, and L plus acting on this psi gives me. So I am able, this algebra that I have done is basically I've tried to write down L square in terms of these quantities, and then your life becomes much simpler, because you know that L plus acting on this L, psi Lz max by definition goes to 0. This quantity, we said that it is just Lz acting on it is h cross. Okay, maybe I shouldn't take, okay, square, sorry, we called it L square, H cut square, L square, psi Lz max. And this quantity is, of course, just LH cross psi Lz max, right? So if you just combine these things together, it should tell you that L square acting on psi Lz max is simply given by H cross square L into L plus 1 psi of Lz max, which tells us this implies that lambda, which is of course the total angular momentum of that state, and remember, acting with L plus and L minus can never change this total angular momentum of the state. That was our one of the first thing we have established. So whatever we have found out, it is still the total angular momentum of the system, which was still given by this quantity called lambda. So we have an expression that lambda is given by H prime of L into L plus 1, right? Now, this is not only the only thing that you can do. There will also be, you cannot also, like you cannot go up and up infinitely because of this condition that Lz square has to be less than L square. You also cannot come down infinitely, because after all, at some stage you will cross zero and it will become negative. And if you can go to more and more negative Lz, the Lz square will then again start rising, and you might violate the condition that Lz square has to be less than equal to L square. So at the bottom, there also has to be a minimal Lz eigenstate. So there must be also a minimum Lz minimum eigenstate, and this cannot be lowered further. Okay. So all that we are saying is that now there is a new state which we called the lowest Lz state. Let's call it psi Lz minimum. And the properties of this is that the z component value of this Lz minimum is given by some, let's say, L prime, okay, which is different from the L that I used previously, L prime H cross of Lz min. Okay. Again, L is some number. We know because the angular momentum shifts in units of H cross, L prime H cross will have the right dimension of angular momentum. So you can always write down this minimum or maximum angular momentum in terms of some number L or L prime times H cross. This is without any loss of generality, right? And the important thing is that L minus acting on this Lz mean would be 0, because again your your postulate is, just give me a second, I need to take this call. Okay, sorry for that. I had to take that call. Okay, so now with this understanding, we can now play the same game as before. We can, like before, we can ask what is the L square value, of the state Lz mean. And to do that, you first write down L square now in terms of the other combination, which is L plus L minus plus Lz square minus H cross Lz. So this is like very similar to what you had over here, and I could just write it down because okay, so there will be an Lz square. Yeah. So you see, you look at this expression over here, and we are just rewriting that same expression now with a negative sign, which is the obvious thing that will happen. And if you play this game, you will figure out that this lambda is now in terms of this L prime given by L prime minus 1. Okay. So previously you had, okay, I had a different coloring. So let's match coloring. Why not? When you have so many colors, when I teach on a chalk and a board, I do not get this pleasure. So at least make best of the worst situation. It is this kind, right? So lambda is equal to h square in terms of this L prime into L prime minus 1. But again, let me remind you, moving from this L max to this L min, you have just repeatedly used the L minus operator. And in the usage of L minus operator, the total angular momentum, the value of lambda never changes, because both L plus and L minus commutes with L square. So while this is an expression for lambda, this is also an expression for the same lambda. So we know by comparing these two things, A and B, we come to this conclusion that L prime is equal to minus L. That is the only possibility. Okay, only then can these two things be equal to each other. The other possibility is, of course, L prime is equal to L plus 1. So the other possibility is, okay, maybe if you want, let me keep that there. Other possibility is L prime is equal to L plus 1, but this is not acceptable. After all, L prime corresponds to the minimum value of the angular momentum Lz, and L corresponds to the maximum angular momentum, and this will, and therefore your general understanding is that L prime has to be less than L, right? So this violates L prime less than L expression, so we neglect it. So the only viable solution that you get is L prime is equal to minus L. And this is now very interesting. Again, if you draw that picture that we were drawing previously, now you have some more information. First, you have this information that the total angular momentum can always be written as some h cross square into L plus 1. But not only that, if you now look at the Lz component, so this is L square, and now if you look at the Lz component, you now know that the Lz component is bound. It is bound between some L and some value minus L. And between them, you have the discrete states which have specific eigenvalues like L minus h cut, L minus 2h cut, L minus 3h cut, and so on and so forth. Okay. So this is the structure. Sometimes, by convention, people use the, these eigenvalues are represented not by mu, but, typically using something called m. So maybe, I don't know, I'm tempted. Should I use m? Maybe we should use m. So the corresponding eigenvalue, so this is the corresponding eigenvalue here, and the corresponding eigenvalue here is going to be written as mh cross. And in that case, maybe, wait, this is not consistent. So the way I should write this is, sorry, this is L minus 1, this is L minus 2, this is L minus 3, and so on. This is how the value is. Okay. So if you take a, so what I'm saying is that you can now define something called L. Now, if you know what is L, the value of lambda is fixed, which is L into L plus 1. And the value of what we were previously calling mu is now given by mh. Okay, so mu is equal to mh from our previous notation. Maybe we also write that. Mu is equal to mh. And the values that m can take are these. It can be L, it can be L minus 1, it can be L minus 2, it can be L minus 3, and so on and so forth. So the values that m can take is plus L, L minus 1, L minus 2, so on and so forth till minus L. So you see, what this is implying, a very important quantity, a very important result that you get from this structure is the following, that you move from L to minus L using n integers, right? Whatever this n is, you can always, n maybe 2, 3, 5, whatever, but you will always move through integers between plus L to minus L because of this structure. You start with L, then L minus 1, L minus 2, L minus 3, and so on and so forth till you reach minus L. So typically you will pass through L integer, which implies that 2 times L is an integer. So L is something like n by 2, and which also now tells us that the possible values of L can be 0, half, 1, 3 by 2, and so on. So you are able to find out what are the possible angular momentum states that exist anywhere in all of quantum mechanics. Okay, that is what we are doing here. Without even knowing what state we are talking about, whether it's that hydrogen atom or something else, we don't care. As long as it is a quantum mechanical state, we are now able to fix the maximal information of angular momentum that you can find out. The maximal information is you can know lambda and you can know mu. Lambda will be given by h cut square L into L plus 1, and mu will be given by m times h. Not only that, this L is not just anything. This L can only have certain fixed values. It can either be 0, half, 1, 3 by 2, so on and so forth, and nothing else. And the m, once you have fixed a value of L, will range between minus L to plus L in steps of 1. So just to give you some example, to make this a little bit more, clear, let me give you a few examples. So any system can be, okay, let's say the angular momentum of any system, maybe that is more clearer. The angular momentum of any, and this is the key thing. We did not solve any Schrodinger equation for a specific problem. No, this is general algebraic treatment. The angular momentum of any quantum system, whatever it is, a particle, a atom, something weird, doesn't matter, can be described using 2 quantum numbers, right? L and M. So let's look at an example where L is equal to half. So M will move from minus L to plus L in steps of 1. So it can only have two possibilities. So this is all the possible things that you can have. Already you know that the L square value is going to be given by half into half plus 1 h cut square. And the LZ value will be either plus or minus half of h cut. Okay. Then if you look at a system which has, let's say, L is equal to 1, the possible values of M is something running from -1 to +1 in units of 1. So it can be 1, 0, -1. These are the possibilities. Again, you know that the total angular momentum of this system is going to be given by 1 into 1 plus 1 h cut square. And the LZ, the possible values of LZ can be h cut, 0, and minus h cut. And now I hope you can figure out what are the other possibilities of these, angular momentum states are. You just go on figuring out what L is equal to 2, L is equal to 3, L is equal to 4, and so on and so forth. Okay. Now, I want to, so you see, we have been able to categorize all the possible eigenvectors of angular momentum, right? We know all the possibilities now. L, it can be any of these values, 0, half, 1, 3 by 2, all that, and M can be these things. So these are all the possible, maybe we just write it down. These are all the possible eigenvalues of angular momentum. But now we want to turn our attention to what are the eigenstates, the eigenvector, the wave function. Okay, so what are the eigenstates of angular momentum? So basically, we want to find out that if you have a system such that L square psi, and now we know it is going to be given by L and M, is equal to h cut square L into L plus 1 psi L and M, we want to find out what is psi L and M. So in order to do this, we go back to the operator form of L. So you remember L was given by R cross P, and this is typically given by the R vector cross H cut by I into the divergence operator, right? I have just written down the operator in terms of the divergence. I hope all of you know divergence, right? I'm sure you know this. So I'm assuming you know this. So, we just, like always, we write it in polar coordinates. There's no reason why you are doing this. You can do it in any other coordinate system, but let's just do it in polar coordinate system because it becomes much simpler. So of course, the radius vector is just in the radial direction. And then you have the divergence vector. The divergence vector is like 1 by r del r into r cap plus 1 by r sine theta del theta. Yeah, okay, so let me check. This is something that I can never remember. There is no sign. That's what I was worrying. And there is no 1 by r. I am terrible at this. Del theta into theta hat plus 1 by r sine theta del phi hat. And then, of course, you can now take the cross product. You already know that the cross product of r with r goes away, so that the derivative with respect to the radial direction will vanish. And then if you are interested in L square, it is just L dot L. You should get your familiar expression. I think you have done this. I think Rohan has discussed this. 1 by sine theta del theta sine theta del theta plus 1 by sine square theta del 2 del phi squared. So this is the operator that you will get. And therefore, if you want to find out the eigenstates of angular momentum, you just use that expression, that minus h cot square 1 by sine theta del theta sine theta del theta plus 1 by sine square theta del theta times, sorry, what am I writing? Del 2 del phi square, and this is sum Lm theta comma phi is equal to h cross square equal to h cross square L into L plus 1 psi Lm theta comma phi. And you have already looked at the solution of this. This solution is just psi of theta comma phi being equal to some normalization constant depending on this m and L times e to the power of minus m phi and the associated Legendre function Lm cos theta, right? Which are sometimes known as the spherical harmonics. So you see, the spherical or the
Sir, there will be an I in the exponential. E to the
oh
power
yes,
plus
yes.
minus I.
Sorry. Yeah, of course. Thank you, Rohan. Off. But there is a small surprise. What is the surprise? If you followed the discussion done by Rohan, you must have seen that in this case, when you think of L square, the angular momentum as a operator related to real rotation along theta and phi axis, and therefore there is this angular momentum. After all, this operator formation comes because you are assuming now the angular momentum is happening because something is revolving in the theta phi directions, okay, and due to that motion it has some angular momentum. So in this kind of a scenario, you must have it must have been discussed by Rohan that the value of L in this case the possible zero, 1, 2, 3, and so on. So Rohan, did you discuss this?
Yes, sir. It starts from 0 and positive integers.
It is positive integers. Now you see the problem, in our abstract way, when we are doing it, we said that this L can take values like 0, half, 1, 3 by 2, and so on and so forth. Whereas if you find it as a solution of this differential equation, L can only take certain integer values. The half integer parts are missing. Okay, so the ones which are sitting in between, which were previously sitting in between half, 3/2, 5/2, and so on and so forth, are missing. So what about this L is equal to half state? Is it meaningful or not? What about the L is equal to 3/2 state? Is it meaningful or not? See, the point here is that previously, when we were discussing about angular momentum, we were talking about a quantum number describing the angular momentum of a system, and we never kind of mentioned whether this angular momentum is related to something moving in a circular way. From our classical notion, angular momentum arises only if there is something rotating, right? So if there is a rotation, only then you would think that there is angular momentum, and then you have this differential equation formalism which works, and the values that L can take is 0, 1, 2, and 3. The half integers do not have any meaning. However, in quantum mechanics, you can describe something abstract, some intrinsic property of a quantum system which behaves like angular momentum, which means it has the same commutation relationship, same Lie algebra, okay, for people who know a little bit of group theory, like angular momentum, but has nothing to do with actual rotation in space. Okay, so these numbers that are here represents angular momentum due to rotation. No, I'm saying this thing very, very loosely, of course, but more in some sense. And the numbers that are missing here are some kind of an intrinsic angular momentum, which is called spin. And the spin is an entirely quantum mechanical phenomena. There's no meaning of spin in classical mechanics. Okay, this is a quantum mechanical phenomena with no classical counterpart. Okay, so typically, if you are talking about this half, 3/2, 5/2, you typically represent the spin. Okay, so let me just mention a few fleeting points about spin. Now here you typically define total spin operator S square and Z component of spin Sz, and all you do is that you make this statement that Lx, Sx, Sy, the commutation is I H cross Sz, Sz, Sx, and so on and so forth, okay, is equal to I H cross L Sy, and so on and so forth, and S square Si is equal to 0 for all I belonging to X, Y, and Z. But the important thing here is that this S square and Sz are an abstract operator which have these commutation relationship, but we are not going to say that this S square and Sz are represented by something like R cross P. This R cross P thing we are removing. Okay, we are saying that this S square and Sz are not related to R cross P. They are intrinsic. You see the leap that I'm taking. See, I first established at the beginning itself that if it is R cross P, then you have this commutation relationship. And then I figured, without ever then referring back to this R cross P definition anymore, without ever referring to it, I figured out that all the possible eigenvalues of this L square and Lz are given by these combinations, right? L has these values and M can take these values. In this derivation, I never referred to whether you can write that L as R cross P or not. I only relied on the nature of those commutation relationships, which is sometimes known as the Lie algebra. Okay, I was just referring to the properties of the group of angular momentum and what are the possible representation of that group of all possible angular momentum. Okay, and we found out that this is the total set. However, in this description, when we again went back to this L being a representation of R cross P, we found out that L can take only the 0, 1, 2, these integer values. The half integers values which were there in the group, representation of the group, are not present if I demand that angular momentum has to be R cross P. So what we are going to do is we are going to separate them up. We are going to say that angular momentum is a larger set of quantities. Some of them can be represented as R cross P, and for them L can take these values. But then there are some of them which cannot be written as R cross P. They are some intrinsic property of the quantum state, and they are the ones which can take this. Okay, so that I have not yet written down. So for these states, we are going to say that this S square can take values like, so the S square eigenvalue is going to be given by S. Okay, it's going to be given, I'm going to represent it by S. So this is the eigenvalue of S square, and this can take values like half, 3 by 2, and so on and so forth. Sorry, it can take all the values. I'm very sorry. It can take 0, half, 1, 3 by 2, and all such values. And of course, for the Sz, the eigenvalue, I'm going to call it as M of S, and this can take minus S to plus S in steps of 1 as before. But here in this definition, I am not worried about whether I can write down S as some R cross P. I'm not worried if something is actually rotating in real space. It can just be an intrinsic property of a particle, like a point particle can have a speed. So there's no question of it revolving about anything, about its own axis. It itself doesn't have an axis because it's a point particle, right? Even they can have these quantum numbers S and M of S, which are intrinsic property of these quantities and which is called spin. So my basic thing that I want to convey to you is the following: that angular momentum is a larger group of things, and in this larger group of things there are a set which can be represented as R cross P. These are real angular momentum, and then there are ones which have the same commutation relationship, which means they have the same, belong to the same Lie group, but they cannot be represented as R cross P. And the extra thing that you get over here is that if you represent it by R cross P, you do not get the half integer states. But in this case, you get the half integer state. Okay. So I think this is a good place to stop here for today. and maybe tomorrow we'll try to first look at the combination of angular momentum and then move on to other things. So Rohan, maybe we can discuss what we want to do tomorrow after this class is over. Okay, so at this stage, are there any questions or comments on what we have discussed today?
So why spin cannot observe in classical particle case?
Yeah, because spin is an intrinsic property in classical physics. Whenever we talk about angular momentum, you are actually talking about object rotating in space. Okay, so everything is like the standard angular momentum, the way we have defined it. Spin is something which is an intrinsic quantum number of a system, which has nothing to do with rotation. So this object, this concept is not present, for example, in any of classical mechanics. Okay. Ayamdeep, are you convinced, or do you think that
Classically there have a spin which is the rotation about its own axis?
no rotation? Okay, so let's say the Earth is rotating about its own axis. It is not spin in what we are describing. Okay. When the Earth is spinning, quote unquote, about its own axis, what you are talking about is various parts of the Earth rotating about the central axis. So there is physical rotation of object, and this physical rotation of the object gives rise to that angular momentum. Okay. When I'm talking about spin, it's like there's nothing is rotating. Okay, this quantum spin, make this concept clear from now. The quantum understanding of spin has nothing to do with anything rotating. Not rotating about its own axis, not rotating about anything. There's nothing to do with rotation. There is nothing to do with momentum. Okay, so you cannot represent intrinsic spin as defined in quantum mechanics in terms of anything physically rotating in space. It is just an intrinsic property of a system, like its charge. An electron has a charge, right? So this charge has nothing to do with any physical motion. Similarly, the electron has a spin. It is not related to any motion in the electron. It is just an intrinsic property of the electron. But it is a member of the same Lie group that encompasses angular momentum, real angular momentum, where there is physical rotation. Okay. So in classical physics, whatever you call as spin, if you really think about it, it is basically angular momentum of physical rotation of some object. Okay. So you say a top is spinning about its axis. Actually, what is happening is different parts of the top is rotating about its axis. When you say, the Earth is spinning, you are actually not talking about the Earth having an intrinsic quantum number called spin. All that you are saying that the Earth, various parts of the Earth is rotating about its axis. So there is physical rotation. And what we are describing here by spin is an intrinsic quantum number, which has got nothing to do with physical rotation. Okay. Soyandeep, is that clear? Think about it. This is a slightly difficult concept if you have not faced with it previously. Actually, even the first attempts to understand quantum spin by Uhlenbeck and others, relied upon really things rotating about its axis. But then, it was subsequently discovered that that is untrue. Simply because fundamental particles are point-like. It doesn't have any extension in space. So there's no question of it spinning about anything. Okay. So you have to now consider this new thing called spin as something like a charge, okay, of an electron. So it has a charge, it has a spin. These are its basic quantum numbers. Okay.
Okay, sir.
Okay, if there are no further questions, let us just wrap up this discussion for today, and we will again continue from tomorrow at 4:30 p.m. Okay, is that fine?
Yes, sir.
Okay. So Rohan, I'm just leaving, and at some point I will upload the notes. You just place it in the right folder. Okay.
Okay. Okay.
Thank you.
Okay. So tomorrow we will meet at 4:30. I am ending this session now.
Okay.